Today we're going to be making my 3D printer finally move and maybe even print something. If you're in my position and want to get your printer moving as fast as possible, this is not the video for you. There are plenty of other tutorials on how to install Klipper on your 3D printer. Instead, we're going to be doing almost everything from scratch. That means no Klipper, Marlin, or other existing motion control firmwares, and we're not going to be using any existing all-in-one motion control boards. By the end of this video, you'll probably be familiar with how most of these existing components work, so that next time you're tuning your printer's slicer settings, you understand roughly what they're doing under the hood. Anyway, in the last video we completed all the main printer hardware, but the toolhead isn't wired up yet and the back electronics compartment is still empty, so we're going to have to resolve that stuff first. The toolhead will connect to this PCB I made. The top side has a connector to attach to the toolhead. For now, this side is this ugly beige color, which is the bare circuit board fiberglass without any copper on it, since we don't want any metal that can conduct heat to the other side. Later I'll probably cover this with some plastic piece to hide the color. Then on the other side, the signals from the toolhead are split out to a large power connector and a USB data only connector. This will be useful because our Raspberry Pi's USB ports can't deliver all the power that the toolhead needs, so we will need to separately inject the power. The other empty hole in this board will eventually be used for routing the filament tube. Also, in case you're wondering, these grooves on the side are for the screws, but are abnormally large because I messed up the dimensions in the CAD and had to do some PCB surgery with a CNC to change the positioning. Anyway, if we flip over our printer, we can install this board below the motor mounts in the back of the printer with a few screws. To go between the toolhead and the board, I'm going to be making a cable using this IGUS chain flex wire. Wires like these are specifically designed to be flexed many times without breaking. Once I manage to get the outer jacket off, you'll see this silver shielding layer, which if we connect the ground on both sides of the cable, should reduce the noise in our data signals. This is one of the tricks the USB uses to reliably run at high speed. Once I've dug even further down, we'll find that this cable has 2 power wires and 2 data wires we can use to make a full power and USB connection. On each end, I'm soldering on these XT30 connectors which mate with the connectors on the PCBs. I also made these 3D printed strain relief pieces which go over each end of the cable, and after being hot glued together, will hopefully keep the connections from coming loose. Once I'm done with all that, we can install the cable. The cable is probably too long to fit under the top pad of the printer that we'll add later, so that's another thing I'll need to fix in the revision 2 of this. The backside connector is also uncomfortably close to the belts, so later I'll need to adjust the spacing of that as well. Next, we're going to populate the back of the printer. On the left side, I'm going to be adding a Raspberry Pi 4, which will handle all the expensive high-level tasks of the printer. On the right side, to do all the low-level motor control, I'm going to be making a new board. If you watched the last video, I went through the effort of making this very space-optimized board for the toolhead, since I didn't have much space, and weight is an important factor there. This time, I'm going to be making this much simpler board, which isn't as pretty, but is much easier for me to make. I have a few more features planned for this in future videos, so we're going to be making a few revisions of this over time as we test things out. At the heart of it is going to be this microcontroller board, which will take as input commands over USB for the Raspberry Pi. Then I got some of these stepper driver boards on the internet, which come with all the boilerplate components you need to drive a stepper motor. You'll often find these called step sticks, as they are a fairly standardized form factor. I'm going to need 3 of these since I have 2 XY motors and a Z motor. The extruder motor is already handled by the toolhead board. Focusing on just one of these drivers, the important components are going to look like the following. 4 pins of the motor driver will go directly to the motor. If you try to take a look inside the stepper motor, we'll find that the central shaft that spins is attached to a permanent magnet. On the outer walls of the motor are electromagnet coils that our motor driver can turn on and off. The coils are wired together such that there are 2 independent sets of alternating coils. So the 4 pins going to the motor are 2 pairs of 2 wires for each set of coils. Whenever our motor driver energizes one of these coils, the shaft magnet will be attracted to the nearest coil and turned by up to 1 step. If we correctly alternate how we turn on the coils, we can create continuous motion. In reality, the stepper motors are way more complicated than this and can achieve much smaller granularity steps, but this is a good enough mental model for the purposes of this video. On the other side of the driver board are 5 pins we're going to connect back to the microcontroller. First is a UART pin, which is just used during startup to send some serial data to set up things like the microstepping and current limits of the motor. Many motor drivers don't have one of these pins and just rely on other pins on the driver to hard code the behavior. Next is the enable pin. By default, this pin will have a high value indicating that the motor should be disabled. Our microcontroller can flip this pin low to enable the motor. Note that when the motor is enabled, these drivers are fairly dumb and will keep the coils constantly energized. So if the shaft is in the wrong position or if something tries to push it, it will try to snap back to the closest step position. Just note that if it moves too much, it'll get aligned with another magnet pole, so it won't recover. You'll usually hear this being known as skipping steps. Anyway, the next 2 pins are the direction and step pins. The direction pin just tells the motor which direction we want to go. Then, whenever we send a pulse to the step pin, the motor will move one step in that direction. Note that in practice, our gyros have a special setting called de-edge that we can set to 1 during startup using the UART pin. This means that instead of needing to set a normal pulse which requires 2 flips of our pin in software, we only need to flip the step pin once to make a step, and then the next time we flip it back to the opposite voltage level. As a bit of foreshadowing, the step pin is going to end up being the most crucial and time-sensitive signal that we need to control, so most of the rest of this video is going to be ignoring the other pins. The last of the 5 pins is a diagnostic pin. This is the pin that is responsible for enabling sensorless homing by detecting when the motor stalls. The general idea is that using the UART pin will initially configure a threshold such that if the load on the motor crosses this, we believe that it has stopped moving. Then suppose something is obstructing our motor and we try to start moving. After enough steps without movement, our driver will detect that the motor is stalled and send back a high signal. At this point, our microcontroller could choose to stop the motor, and if we're doing homing, mark this as the 0 position. Just note that without additional sensors, the motor drivers can only detect stalling after several microsteps, so this isn't very precise. You could also replace the diag pin with a regular physical end stop, which will produce the same signal on being hit. It will probably be more precise, but has added complexity. With this information in mind, the next steps were to lay out all the wires and KitKat on a PCB design. For the most part, this is what I described, copy-pasted to 3 motors. The large blue and red regions are 24 volt and ground power inputs going to the motor drivers. Then I cut out the board on my CNC and then assembled it. There are also some less important components on here for interfacing with the bedboard, fans, and other sensors we'll discuss later. At the end, we can plug in the microcontroller and separate boards and we're done. Now that we have the boards, we need some way to mount them in the printer. The guidance in the Voron manual is to print out some DIN rail cleats like these that will stick to the back panel with high strength tape. I don't like these since they're fairly tall and take up almost half of the depth in this back compartment. The large height also means that there's going to be a lot of torque on this cleat when I move the printer around, so there is a risk of the board coming off over time. Also, since they're taped on, it'll be hard to upgrade the electronics in the future. The next best thing I found is this full DIN rail mod on the internet. To some extent, it makes it easier to move the electronics around in the future, but it's still fairly tall. What I ended up making instead is this acrylic mounting panel. It's only 3mm thick and lets me plan out the position of everything precisely in CAD beforehand. I made this by first laser cutting out the main shape. Then I have some recessed holes for the Raspberry Pi mount that I drilled out on my CNC. And lastly, I tapped out some threaded M3 holes. If you already have all these tools, you can make one of these in less than an hour. You can also just 3D print one, but that'll take a bit longer. Once it's ready, the Raspberry Pi screws in on one side on top of some spacers. Note that the heatsink I'm using can only be screwed in from the bottom, so that's why we recess the holes so that the screws can be flush with the surface of the plastic. Then the microcontroller board screws onto the other side using the threaded holes. Coming back to the printer, we can remove 4 of the screws holding on the back panel and replace them with longer ones that will go through our electronics panel to hold everything in place. Switching to the bottom side of our printer, the last electronics we're going to be installing is one of these DC to DC buck converters. This board will take as input the 24 volt power from our main power supply and reduce it to 5 volts, which is the most that our Raspberry Pi and microcontroller can handle. Note that most other control boards like the SKR Pico have this built in, so you probably don't need one. Since I'm going to be iterating on this board a few times, it's easier for it to be separate so I don't have to reassemble it every time. The converters that I got came with these holes where you can solder wires or pin headers. Just to make things easier to change around, I mounted these small adapter boards that'll let me use screw terminals with these boards. To install everything, I'm first going to add some Wago connectors that are going to fork off the 24 volt and ground wires from the main power supply. Then I 3D printed this mount for the buck converter that gets taped in place. And then the buck converter can be screwed on top. Now for the wiring, I made this long wire that splits the power connector from the main power supply 2 ways. 4 of the wires will go up from the power supply to the umbilical board to power the toolhead. The other wires will go into the Wago connectors to be forked off to other stuff. Using the next port on the Wago connectors, we'll split off some power to the main control board to power the motors. We'll also need to add wires to give 24 volt power to our buck converter. Note that if you're using adjustable buck converters like these, you'll need to power them on first with nothing attached to the output and measure the output voltage while adjusting this little screw until the voltage is what you want. Once we're confident the buck converter is giving us a stable 5 volts, we can route its output to our Raspberry Pi. Then we can hook up the motor wires. 2 of the other connectors I added are for hooking up to the bed relay and the bedboard that we added in a previous video, so we can also wire those up now. The Raspberry Pi will coordinate all the different boards you have, so I'll hook up the main motor control board to one USB port on the Pi and then another to the toolhead. Lastly, to keep things cool, I'm going to be adding these 40mm Noctua fans. They will be attached using these custom brackets which slightly raise the fans and allow them to be screwed into the electronics panel. Any cables in the way of the fans can be routed below the fan between the screws. At this point, we have two microcontrollers connected to our Raspberry Pi and need to align on some protocol for them to talk to each other. At the hardware level, you should have noticed that we're using USB to connect to everything. To be more specific, this is a direct USB connection between the Raspberry Pi and the CPU on the microcontroller board. USB has a lot of nice built-in features like automatic error detection, flow control, and retrying, so we can for the most part assume that this connection is reliable. Another popular method you'll see on 3D printer boards is to connect via a 2-wire serial, also known as UART. This may be either directly between the Pi and microcontroller, or you might see something like the serial connection hidden behind a USB to serial chip. In short, if you have a UART connection anywhere in your connection chain, you're going to be bottlenecked by that, since it's very susceptible to errors that will need to be detected by the software. If you look at firmwares like Marlin and GRBL, the general strategy is for almost all the computation to run on the microcontroller, so the connection layer can run fairly slowly, since you just need to occasionally send some plain text G-code to the printer and get back some very basic responses. In the case of Klipper, most of the computation runs on the Raspberry Pi, and data is very frequently sent to the microcontroller, so the connection needs to be much faster and more reliable than the Marlin case. If you read the Klipper documentation, you'll find that they first compress each command into a custom binary format to reduce the amount of data transferred. Then this is assembled into messages, which add fancy sync and checksum bytes in software so they can detect errors. And lastly, there is extra software logic for waiting for messages to be acknowledged or to retry them. In my motion controller, we're going to be doing something sort of similar. First, I couldn't be bothered to implement another custom command format, so instead we're going to be representing all of our commands as protobufs, which is a popular open source library often used to exchange messages between servers and data centers. The other two parts I don't need to implement myself since I don't care about supporting serial links, and USB will handle this stuff for us for free. I'm still going to be including a sequence or ID number in each command though. While Klipper implements a sort of RPC-like protocol, mine is implemented strictly with the Raspberry Pi being the client and the microcontroller being the server. In other words, the Raspberry Pi will always initiate requests labeled with some IDs, and then sometime after those requests, the microcontroller will provide responses in some arbitrary order matching each request. Now surely we just need to write some simple code to make the printer move. A good first step would be to figure out how to do basic movements. So let's say we want our Raspberry Pi to tell the microcontroller to move motor 1 by 20 millimeters. First of all, how the heck is the microcontroller supposed to know what a millimeter is? All it can do is issue step commands to the motor. Well, our main two motors for X and Y movements are hooked up to pulleys which move belts to move our tool head. More specifically, we're using 20-tooth GT2 belt pulleys like these. These have pretty standard geometry, so you can usually just find a calculator online that'll tell you how many steps of your motor equal 1 millimeter of belt movement. Know that the z-axis is similar, but is a screw with a known distance that it moves per full rotation. So to move one of our XY motors by 20 millimeters, our microcontroller would need to send 20 times 80, which equals 1600 step pulses to our motor driver. But we don't want to send these too fast since there's a limit to how fast our motor could physically spin. So we'll also need to tell our microcontroller that it should move at say 25 millimeters per second. So that ends up being a rate of 2000 steps per second, or 1 step every half a millisecond. To do this, our microcontroller also needs to have a concept of time. Most microcontrollers have timer peripherals, which are internally attached to a counter. We're going to configure our timer for 16 MHz, so 16 million times per second. The timer will increment the counter by 1. Also, most timers will let you give it some target value and set up an interrupt such that when the counter value hits that target value, it'll run some code on your microcontroller's CPU. In the context of stepping our motor, let's say our microcontroller's CPU starts running the code to step through a motion at counter time 10. It'll first do a little bit of work to flip the step pin once, then it'll tell the timer to run this code again at the next step's time. In 16 MHz timer units, our half a millisecond step duration is 8,000 ticks, so we will set up an interrupt to run at time 8010. Then the CPU can chill until that time comes. Once the interrupt triggers, the code will run again and repeat the whole process until we're out of steps. The main issue with this comes if our CPU is already interrupted to do something else. By default on ARM CPUs, if this happens when our timer interrupt comes up, the interrupt will have to wait until the other code is done running. Only after that is done can our stepping code run. In this example, our step was done 5 ticks late. This effect will be more noticeable if you're moving very quickly and may appear as choppy motion of the motor, or in the worst case as skip steps. On ARM CPUs, you can partially solve this by assigning a higher priority to your timer so that it can interrupt the other code. If your CPU has multiple cores, moving the stepping code to another core is also another option. Neither of these will completely solve the problem though, since you will inevitably have some other non-interruptible code, like the code that adds more steps to the step queue. On microcontrollers like my NRF52, there are also fancy hardware peripherals that I set up that allow the counter to completely bypass the CPU and directly flip the value of the pin. Then the CPU only needs to change the target counter value, which isn't as time sensitive. So if you do all that, you'll get a motion that looks something like this. So that's not very useful yet, since we need to figure out how to move in the X and Y directions and not diagonally. This behavior is caused by the Core XY belt setup of our printer, and you can also reproduce this just by moving the belts manually by hand. So the first motor will move us along one diagonal, and the other motor will move us along the perpendicular diagonal. Moving both motors in the same direction moves us along X, and if you move them in opposite directions, we move along Y. If you Google Core XY, you'll probably find the Core XY website, which distills this down into equations our software can use. Basically, if we want to move in something like a square in the XY directions, then for every point along the path, we need to plug it into those equations and generate the A and B motor positions that we need to follow. I should mention that Klipper actually does this in the opposite direction, but that's too much to explain for this video. Anyway, if you do this in real life, here's what it looks like. So the problem with this square is that currently it's going at a constant velocity, so at each corner, it's starting and stopping with infinite acceleration. You can intuitively think of this like slamming the brakes on a car really fast. If you have the motors energized on your printer, you can see by pushing on your toolhead that the belts are spring-like. So even if your motor did immediately stop rotating, if we're going really fast, the belts will still move beyond the target position and then bounce back. To fix this, most firmwares will implement a trapezoidal velocity curve. First, you slowly ramp up to your max speed. The slope of this line will be your max acceleration setting. Then you cruise at some constant max speed, which is your feed rate. And then you need to slow back down to 0 velocity at the end. Note that if you try writing code that does this, there are a bunch of edge cases you need to handle. The most obvious one is that if the movement is too short, there will be no time to have a cruising stage, since you don't have enough time to fully speed up and slow down. Anyway, to be able to actually move along this curve, we're going to need to teach our microcontroller how to move in a constant acceleration curve. In the last section, we taught it how to follow a 0 acceleration curve, since the time interval between steps is constant. If you do some physics math, you'll find that calculating the time between steps in the non-zero acceleration case gets a bit complicated. This is mainly a problem because our microcontroller is especially slow when it comes to doing non-integer operations, and it is extremely slow when it comes to calculating square roots and divisions. So it's unlikely it'll be able to calculate this fast enough before the next step needs to be pulsed. There are two main approaches you should probably be aware of to solve this problem. The first is to hack the math to work with the slow microcontroller. Some firmwares will try to break up the acceleration curve into multiple flat curves of constant velocity and do some lower level smoothing. Some other firmwares use a more efficient integer arithmetic only approach to calculating the step times, like what is described in this paper. If you're working with a firmware like GRBL, Marlin, or Prusa firmware, they're going to be using some variation of these tricks, since all their code has to run on the slow microcontroller. Generally, the issue with all of these is that once you implement them, you're only going to be able to do constant acceleration moves, so you're going to need to pile on even more hacks if you want to do things like S-curves, input shaper, or other non-linear geometries like delta printers. I'm not going to talk about these much more in this video since I didn't implement any of them. Instead, we'll be using the method that Klipper uses to represent motions, which is as curves where the start time of each step is calculated like this. We just need to pre-calculate the initial step time, duration, and add value, and then on the microcontroller, these simple equations involving only fast integer addition operations are used. As an example, let's say we want to travel along a curve that looks like this. First, on our Raspberry Pi, we're going to run the raw physics equations to calculate the time at which each motor reaches the next position to get a full list of step times. Note that Klipper uses a more complicated way of doing this based on an iterative solver, but at least for this simple example, these both achieve the same result. In theory, if our USB connection is fast enough, we could just send these raw step times to the microcontroller, but since we would be sending thousands of steps per second, it would take a bit of load off the microcontroller if we could compress them a bit. If we do a basic fit of the Klipper-like curve to these, you'll get something like this. They don't line up perfectly well, so instead we're going to need to get more clever and split up the motion into multiple curves. The algorithm that Klipper uses for this is way too complicated to explain and more optimal than what I need. So what I ended up doing to compress these is just using a classical bisection algorithm. First, I try to fit a curve to the entire list of steps as we've already done. If the points are too far away, I split the list in half and try to fit each half. If that doesn't work, we keep splitting things in half. Unfortunately, by solving one problem, we created another one. I'm currently trying to move my printer in a circle, but it's really slow. Basically, all firmwares and slicers will just split up the circle into a list of lines to make the math much easier. This means that with our current approach, the printer will come to a complete stop at each of these line segments. Intuitively, you'd think that if we make a smooth turn, we shouldn't need to slow down that much. But mathematically, this is a point of infinite acceleration where we instantly stop moving in one direction and start moving in another direction. One of the hacks you'll see to make this work is to allow up to some amount of speed to be instantly lost when cornering. You often see this parameter known as jerk. This shouldn't be confused with the derivative of acceleration, which is also called jerk but is unrelated. The other algorithm you'll see is the junction deviation algorithm. You can read this blog post if you're interested. Basically, this makes the cornering speed proportional to the angle between the two lines. If you're using Klipper, this is scaled by the square corner velocity parameter in the config. Anyway, now we can handle circles. The last thing we need before we can start printing is to home our printer so it knows where the 0 point is in space. For the most part, my procedure is pretty standard. We move in the negative X direction until we see the motor stall, then we back off and do the same thing for Y. For Z, we raise the bed until the PZ probe detects a touch and then the motors need to be stopped. Since this video is already way too long, mesh bed leveling will happen in the next video. So I'm out of excuses to not print something, so here we go. I sliced this pretty standard calibration cube and sent it to the printer. If you made it this far into the video, you might be under the illusion that I actually know what I'm talking about. Well, here's all the prints that failed before that one. For the first two, I ran into floating point numerical issues, which made the extruding just stop after a few layers. This is mainly because the extrusion step position is constantly going up and eventually becomes a very large number. The G-code that Prusa Slicer generates actually adds these lines in the G-code to reset the extrusion position to avoid this issue. But in my first few attempts, I just decided to ignore these because surely it's not important. The next few attempts look like this because I messed up implementing that reset G-code line and ended up locking the Z position in the same place forever. Then we have this one which finished but skipped a bunch of steps since I didn't yet have the timer interrupt prioritized. Then we had these which failed to print because I was running the printer firmware on my main computer via a long USB cable. TLDR is that if you connect two USB devices without isolation running on different power supplies, you may run into interference problems due to ground loops. Either that was the issue or my USB hub had some other issues. When everything is running from the Raspberry Pi, everything's completely stable though. Then I printed this one, which is a good reminder that you need to have NG code to lift the nozzle after the print is finished. To wrap up, the final cube came out fairly well. It's supposed to be 20 by 20 by 20 millimeters and it comes pretty close. The first layer is also pretty smooth and I can very repeatedly make these now. Next video will be all about cranking everything up a notch to bring the quality and speed up to modern standards. And don't worry, stuff like pressure advance and input shaper is still on the roadmap. Bye!